Hey everybody, welcome to my first lecture in the set theory section, very deeply titled sets. What we want to do today is develop a formal language for describing collections of objects. And what we're going to call those collections of objects is a set. It needs to be well defined enough so that I can tell what is or is not in that set. And for instance, like if I said the set of all cats in the world, I would know that I am not a member of that set, but the cats Nico and Maki, they would be in that set. We call the objects that are in these sets elements, and sets are typically denoted with a capital letter, while elements are typically denoted with a lowercase letter. And then you've seen this notation before because we've been talking about like this arbitrary number k is in the integers. So integers would be another example of a set. So we say that a element is in a set A using that little backwards E sort of, or not backwards E, backwards epsilon looking thing. And the element B is not in A by putting a slash through that little epsilon thing. Okay, let's look at some examples of sets, discuss what is and is not in them. So first off, we've got a set A. And that's just the numbers 1, 2, 3, 4, and 5. So things that are in this set. The number 1 is in this set. The number 2 is in this set. 2.5 is not in this set. And 6, kind of fitting the pattern of 1, 2, 3, 4, 5, is not in this set either because the set ended at 5. Next, we've got B is equal to 2k, where k is in the integers, and hopefully this looks familiar. This would be the set of all evens. So for instance, 2 would be an element of B. That would be when k is equal to 1. However, 1 itself is not in B because you can't get an integer times 2 and get 1 out. And then last of all, my favorite set, spoons in my house. So my spoon from breakfast, sure, that's short for breakfast. That would be in C. However, your spoon would not be in the set C because that is not a spoon in my house, at least I hope. So moving on, we can talk about some important sets. We've heard most of these. You probably haven't heard of empty set before. We definitely haven't discussed it. It's denoted with this fat O with a slash through it, and it literally just has nothing in it. Big whoop, it's empty. Who saw that coming? Then I know we've talked about natural numbers. Depending on who you talk to, 0 might be included. But for the purposes for us, we're not including 0. And then we have integers, so that would be negative, that would be positive, 0 definitely included, and it's all the whole numbers, nothing like 1.5 in there. Rational numbers, we have formally defined this one before. Real numbers, so I guess we haven't really technically defined that one, but we've worked with them enough that you guys should know it's like all possible decimal expansions, so like 2.0 would be a real number, but 2.000001 would also be a real number, and 2.1 going on forever would be a real number. And then complex numbers are just numbers that have this extra piece of an I. So like any real number plus something involving I would be a complex number. Indeed, real numbers are actually part of the complex numbers, just like natural numbers are kind of like a specific part of integers. Integers are a specific part of rational numbers, and rational numbers is a specific type of real number, and real numbers are a specific type of complex number because nothing is stopping B right here from being 0. So if B is 0, then we have all of the real numbers, and when B is not 0, that's what we typically think of when we think complex numbers. Not super important, but I wanted to introduce you to that thought Oops. Because you don't really get introduced to that thought anywhere, and then they expect you to know it later on. So I talked about it briefly. So next thing that we want to talk about is we want to talk about when two sets are equal. So we say that two sets are equal, and we denote it with normal equal sign. And they're equal when X is an element of A, if and only if it is also an element of B. So A and B have the exact same elements in them. For instance, if we look at our first example, we have elements 1 through 5. And sure, set B in this case has those elements backwards, but it doesn't matter what order they're in. The important part is they both have the element of 1 in the set. They both have the element of 5 in the set. They don't have anything other than the numbers 1 through 5. And then same thing about repeating. So we have 1 shows up twice in this set, but it only shows up once in this set. And then 5 shows up like 3 different times, but it only shows up once. We don't care about repeating, we just care whether it's there or not. So when you see sets, you're never going to see them written out like this. They're always concise. The element shows up once because if it repeats itself, that doesn't add any new information. Something that would not be equal to each other. We've got 1 through 5, but then 1 through 5 and 7. Obviously, 7 was not in that first set, so they are not equal. And then this one's kind of like odd to think about, in my opinion. So this would be, we already talked about it, the set of all evens. But if you take it and just put a +2, that's just another even. You haven't gotten any new evens you're just starting at a different place. So like the first even you might think of in here would be 2, whereas the first even in here you might think of would be like 4, because you're using the integer 1 in both cases. And just to convince you, I will prove that these sets are equal later. And then last example, the empty set is not equal to the set of just 0, because 0 is an element. It is a perfectly valid element. It's actually a pretty great element, but he's in there, and so it is no longer empty. All right, with that spiel, now we're going to talk about subsets. So we say that A is a subset of B if every element in A is also an element of B, but this is not the same as being equal, because we're not guaranteeing that B also has all of A's elements. It says nothing about that. And then we're going to denote that with this little C-looking notation. Your book used this with the line under it. Nobody writes that. Mathematicians, I guess, are just too lazy to be bothered to write this little line, because what it says is it is a subset or equal to, and we're just too lazy to write that. Some examples of some subsets would be, remember this set from earlier, 1, 3, 5 was not equal to 1, 3, 5, 7, but it is a subset because all of the elements over here are elements over here. And then the next set we have is 1, 3, 5 is a subset of itself, because all of the elements here are indeed elements here. Doesn't matter that they're equal. The important part is everything over on the left is also included on the right. And then just kind of like reiterating what I said earlier, the natural numbers is a subset of the integers. Now we have formal language to describe what I was talking about just a few seconds ago. Natural numbers are all found in the integers. All the integers can be found in Q. All the rational numbers can be found in the real numbers, and all real numbers can be found in the complex numbers. They're all subsets going like that. And yes, that does mean that the natural numbers does end up being a subset of the complex numbers. It does work like that. A proper subset is going to be when we get into the possibility that they're not equal anymore. So we say that A is a proper subset of B if it's a subset of B and B has elements that aren't in A. We denote this using the subset notation with this little slash through the bottom. There, that may be hard to see, so it's real big. It would look like that. So we typically only use that when it's like really important that A and B aren't equal. We mostly just use the normal subset notation. For example 5, we have that 135 is a proper subset of 1357, but we don't really care that much. It's if you use just regular subset notation for that, I'm not going to bust you on that. Not that important. But we will see times when it is important, and I will point out when it is important. So far, we haven't done anything to do with proofs, which is what the bulk of this class has been all about. So let's bring it back to proofs for a moment. So we have ways of proving, so we've talked about like defining equal and defining subset and stuff. We have ways to prove that A is a subset of B. What you do is you take an arbitrary X in A, and then you manipulate it with all the definitions that you have. It's a direct proof, so you manipulate it using definitions, blah, 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 and you eventually find that this X belongs to B. Since we didn't put any restrictions on X, it's nothing special. It was just some random element in A, and it was, most importantly, arbitrary. So there we go, back to that like universal generalization, I think it's called. We have that for all X in A, we have that it is also in B, which means every element in A is going to be an element of B. Therefore, we say that A is going to be a subset of B. For instance, let's prove that the integers are indeed a subset of the rational numbers. So we start off with let X be an element of Z. I would like to point out that X is going to be equal to X over 1. And then that's getting kind of close to our definition of rationals. So since X and 1 are integers, and 1 is not 0, which is what we need when we're talking about rational numbers. We need denominators to not be 0. We have that X, which is equal to X over 1, is going to be an element of the rationals. Therefore, Z, that's not how, there you go. The integers is a subset of the rationals, and we are done. All right. So I like to call this kind of element, this type of argument element chasing. You start with him here, and then you just chase him all over the place until you eventually chase him into the other set where you want him to be. Now that we've discussed how to do that, let's move on to proving two sets are equal. This requires the subset argument. It's kind of like, remember we did the if and only if. It always came in like two pieces where you like prove the forward way and you prove the backward way. Same thing for proving sets are equal. You do that A is going to be a subset of B, and then you turn around and say that B is going to be a subset of A. Remember, being a subset doesn't prevent them from being equal. That's proper subsets and proper subsets only. So we prove that A will be in B, so B has all of A's elements, but then we prove that B is in A, so A has all of B's elements as well. So they both contain all of each other's elements. And then once we have proven both of those statements, we very quickly conclude that A is going to have to be equal to B, because there's no other way to like have both of them contain each other. For example, let's go back to this, all the evens and all the evens rewritten. Let's prove that so that you feel very convinced that these are indeed the same set. So I guess we'll start with, I'm just going to number these. If we start with K is a -1, that would be like a -2, 0, 2. And then same thing, if we start with L as -1, you would get like 0, 2, 4. So it's right from here, you're just like, okay, I could kind of see, like maybe if we do one more in each direction to be extra convincing. Can definitely see that this is the evens, and I can definitely see that this is also the evens, just kind of offset funny. Let's prove that they're equal. So again, just like when we did the if and only if stuff, we're gonna like indicate which direction we're doing first. Let's go ahead and do this subset direction. So we have an element that we're gonna say is an A. That by definition of our set A, we can conclude that there exists a integer k such that x is going to be equal to 2k. Now we're going to try and manipulate this. We want it to end up looking like a 2L plus 1. So, that's odds, 2L plus 2. This is the goal. So I'm going to manipulate this a little bit. I'm going to say that x equals 2k, and then I'm also going to subtract a 2 and add a 2. So now I have my plus 2, but it doesn't really look the way I want. So I'm going to say group these guys up together and factor out a 2, which is going to leave me with k minus 1 plus 2. And then that k minus 1, it can be my L. So 2 equals L plus 2, where L equals k minus 1, and it is an element of the integers, just like we wanted. So then x, which is equal to 2L plus 2, is going to be an element of B, and that's one of our directions. So we have A as a subset of B. And did I? No, I did not leave myself space. And then we shrink this argument because it was a little bit large and in charge right there. We move on to the other direction. So now we're going to start with something that's in B, and we're going to push it into A. So let x be an element of B. Then by definition of being in B, we have that x equals 2L plus 2, where L is an integer. Then we can say that x is equal to 2, and I'll just factor, because I'm looking for just 2 times an integer like that. So I'm going to factor the 2 out. And then I can say that L plus 1 is our k. Where k equals L plus 1, but L was an integer, 1 is an integer, so we get to say that that itself is an integer. So then x gets to be an element of A. So B is now a subset of A. Shrink this down a little bit. Therefore, since they're both subsets of each other, A equals B. So I don't know about you, I saw this argument for like the first time when I took this class, and I was like, oh, that's so cool. But I'm a nerd. What can I say? Last topic for today. We're going to talk about sets of sets. Now, a set is just an object. So since sets are collections of objects, there's no reason that we can't have a set of a collection of other sets. For instance, this set A has the set of 1 as an element. It has the set of 1, 2, and 3 as an element, and the set 3, 4 is another element. We would not say that 3 itself is an element of A, and we would not say that 1 is an element of A. The set of 1 is an element of A. So like this entire thing, parentheses and or curly brackets and all. Like if you think about a set, as being the trash can, and then elements are going to be what's inside the trash can. You would say that, like, if we say that this guy is purple, we have the first element is this trash can with a 1 in it. We have this element is the trash can with 1, 2, and 3 in it. And then the last one would be a trash can with 3 and 4. So each of those colored trash cans inside the blue trash can would be the element in the set. I feel like that's like kind of okay for most people, and then things get like really wonky when we start putting the empty set inside of things. So let's go ahead and talk about that real quick. Is the empty set equal to the set that contains the empty set? We're going to go back to our trash can metaphor. We're going to say that the empty set would be a trash can, but it is an empty trash can. There's nothing in it. Now, the set, I'm going to make that green, that contains the empty set, that's going to be equal to, let's see, the big trash can, which is green, because it is the set containing, and then the empty set, I've already said, is a trash can. So it's like having an empty trash can inside of a trash can. Is the green trash can empty? No, the green trash can isn't empty. It has a trash can inside of it. The trash can inside, the blue trash can, that guy's empty, but the green trash can would not be empty. So the set containing the empty set is not the same thing as just the empty set itself. Okay, hopefully that wasn't too confusing of a note to end on, and I'll see you all next time.